In this lesson we analyze an alternative unsupervised clustering approach, named hierarchical clustering. A drawback of k-means is that it requires fixing the number of desired clusters. However, in some application this is an information that we do not have. Actually, it may be the primarily interest of the analysis to discover how many subpopulations we have. Hierarchical clustering is a non-parametric clustering algorithm which does not need to pre-specify the number of clusters. The only input required is a similarity matrix. This is a square matrix whose size is the number of objects to be clustered. Each entry of this matrix must be equal to the distance between any pair of observed data. Similarly to k-means, such distance may be the Euclidean one or any other notion of distance. The distance matrix D defines how close objects are, regardless of their cluster assignment. To run the algorithm, we also need to specify a notion of distance between clusters. The most common one is the complete linkage, which defines the distance between two clusters as the maximum distance between any pair of their points, 1 point per cluster. Looking at the example in the slide, the distance between the two clusters is the distance between the 2 points connected by the red line. An alternative is the single linkage, which takes into account the minimum distance. Hence, it is more sensible to noise. Let's see how the algorithm finds the final partition. First, it starts from a single cluster and split it into two smaller clusters that must be as far as possible, according to the adopted notion of distance between clusters. This step ensures that the two subpopulations will be as much heterogeneous as possible. Then, such step is repeated until each object forms a cluster of its own. This approach is called divisive clustering. The opposite strategy is also possible, called agglomerative clustering. The final output of the hierarchical clustering is a tree, named dendrogram, which is displayed in the slide. This tree can be horizontally pruned to identify a specific clustering, whose number of clusters is equal to the number of branches that have been cut. The dendrogram also identifies the best number of clusters to represent the whole population. Indeed, the longer is the branch of the tree, the stronger is the evidence for the corresponding number of clusters to be the most suitable for the data. Let's see some examples. The red line represents the height where we cut the tree. By pruning in this position, we select two clusters because the red line intersects two branches. This is also the most suitable partition for our data because the branches are the longest of the tree. The figure on the right shows the obtained clusters with two different colors. If we cut slightly below, we select three clusters. This solution is worse than the previous one because the branches are shorter. In fact, look at the plot. It is difficult to justify why red and blue dots are not part of the same subpopulation. The suggestion is to always visualize the partition that is generated. As in cluster analysis, it is important to have interpretable clusters. In this third case we are cutting in a position that gives 5 clusters. This is probably overfitting the data, selecting very small populations. Keep in mind that the higher the number of clusters, the more difficult it is to give a reasonable interpretation of all clusters. Usually, a relatively small number of clusters is preferred. And now, let's apply this technique in R using the same data already considered to test the k-means. To perform hierarchical clustering with R is very simple since it only requires a single input, which is the distance or similarity matrix. To compute such matrix, it is enough to use the function dist on our data. This function automatically computes the distance between each possible pair of points in the dataset. In the code, the outcome of the clustering is saved in a variable named fithclust. To visualize the dendrogram, we can use the plot function as shown in the slide. Besides the first argument, the others are added only to show a better-looking plot, but they are not mandatory. Moreover, we can use the rect.clust function to visualize where we prune the tree. To use this function, it is enough to put the variable containing the clustering as first argument and select the number of clusters. As the second argument, named k, in this case we select 3 clusters because it is the partition associated to the longest branches. This produces the 3 rectangles displayed in the figure. To actually prune the tree and select a partition we can use the qtree function, which needs the same arguments of the previous analyzed function. Its output, named estimated clustering in this case, is a vector containing the labels that define the final partition. This can be plotted as we did for the k-means. Please go back to such lesson to check how adapt the code to your problem. The final partition is the same we obtained using the k-means with k equals 3. Generally, the two algorithms find different solutions. However, this example is so simple and clusters are so well separated, that both methods arrive to the same conclusion. And now, it is your turn. You have to repeat what reported in the previous slides. Data are taken from a medical study which aims to cluster patients who underwent thyroid operation. Your task is to perform a hierarchical clustering analysis and choose the most suitable number of clusters.